Hi everybody, I'm Andrew Payne. I'm co-founder and CEO at E11 Bio, and I want to talk a little bit about Connectomics and AI safety today. So, humans are our only existence proof for aligned general intelligence, and nobody knows how to align AGI. It follows that it would be very helpful if we were able to leverage the thousands of neuroscientists that are working on studying this particular form of general intelligence in order to accelerate progress. This could be a big opportunity if it could work. So there are three areas that I want to highlight where if we apply the neuroscience community's efforts towards the problem of connectomics, we could potentially unlock some really transformative options. The first option, the first area I want to highlight is brain-inspired AGI. So questions that we might want to ask if we are trying to learn from the brain and apply it to AGI is, for instance, for illustrative purposes, can we find specific circuits that encode social instincts? Steve Burns has a long series on the Alignment Forum, which goes into this in great detail, so I encourage you to check it out. But the sort of things that we might discover, hypothetically, illustratively, is that there might be circuits that go from the hypothalamus or the brainstem to the cortex and exhibit supervisory or steering control over how we learn. So this is the sort of thing that we would love to study if we had the tools to do it. Okay, the second area I want to highlight is whole brain emulation, which we have been talking about quite a bit. We're still not ready to look at a WBE of a mouse. We don't have a mouse connectome, but we know that already connectomic constraints can be super important for modeling and for emulation. We can see now from the fruit fly connectome, which came out last year, that you can do very accurate predictions of neural activity by constraining your models with the empirical parameters that you observe in the mouse connectome, in the fly connectome. So this is an opportunity to reduce the number of freak parameters in your models, which could be really impactful, not just for sort of like first principles WBE, but also for these lo-fi or soft approaches that people have been talking about today and will continue to discuss. Okay, the third area I want to highlight is BCI. This is not about AI alignment per se, but as a couple of people have mentioned, it's really important to be able to keep humans in the game in order to buy as much time as possible to explore different opportunities for AI alignment. And so I can see this working in two ways. One is in the traditional map, modulate, and measure paradigm, where we can find different targets, finer targets for neuromodulation, which is super important as people develop finer control over how you can perform neuromodulation. And then a second area that I think is super important, which Max touched on, is in biohybrid BCI, you want to engineer cells and then introduce them to exogenously start making connections with native tissue. This happens randomly. What you would really like is to have fine cell type specific control over how these engineered cells reintegrate in this biohybrid BCI model. So being able to do that is a key part of the design build test loop that we are missing right now. So those are three areas where connectomics could be helpful. One question that we always want to ask is on what time scale and can we compress it? So in the next couple of years, I think it would neuroscience, as Patrick said, is slow, and on the other hand, a great deal of the probability density is still spread out over decades. So even 1 decade is well within the time frame that these approaches could start paying off. Okay, so these are applications that connectomics could impact. One question that follows is are the tools ready? Is the technology ready to start adding value in those areas? And in order to answer that question, I need to tell you just momentarily about the current paradigm. We use electron microscopy right now. This involves serial slicing of stained mouse tissue, followed by computational stitching and reconstruction. This has obviously paid off super well for the fly connectome, as well as for cubic millimeter scale human and mouse tissue, including a pretty spectacular announcement of 1 cubic millimeter of human tissue a couple of weeks ago in Science. And the next frontier for EM is the whole mouse brain, which is, a 500-fold scale up. And the technical challenges are such that most practitioners think it's going to be 5 or 10 years before you can do it. So, a couple of years ago, some friends and I got together and started thinking about, what could we do in order to accelerate progress in connectomics as quickly as possible? And how do we make it sure it's, relevant to alignment? So we founded E11 Bio, which is a philanthropically funded startup or a focused research organization that is building next generation tools because we think new technology is what's needed to make progress go as quickly as it can. So, in a nutshell, the tool that we've developed works like this. It's very different than traditional approaches. It's based on viruses. You deliver them to the mouse brain. You perform serial iterative imaging and staining and destaining of hydrogel tissue. And then you tie it all together with computer vision and barcode matching algorithms. And why is this important? In the current approach, you have EM, which looks at morphology. In alternate approaches with barcodes, you can iteratively probe every pixel one after the other in order to build up a color vector. And that allows you to connect neuronal morphology across large spatial gaps, which is super important for targeted connectomics, for reducing the cost of segmentation, and for getting molecular information as well. And I can go into detail on that. So the team has been working super hard, and we are now at the point where we are mapping brain tissue in the mouse using this method. We're super excited about it. I would love to go into details after the talk. We have a pretty cool demo that I would love to get into. And I just want to acknowledge the team has been working super hard and has been making a ton of progress compared to what we might have done otherwise in academia or in other areas of industry. And just one last thought. One question that we often want to ask is how can we compress the timeline as much as possible? The way that we've been approaching optical connectomics is doing it stepwise. We de-risk one piece after the other. But I think it's really interesting to think about how quickly we could get to a mouse connectome if we put all of these projects going in parallel. This might require sort of a fast R&D approach of the kind that Juan was talking about earlier. So I'll leave my conclusions up here, and thanks everyone.
Awesome. I see many demos emerging. I want to see if there's someone in the back, because I've been in the front a lot now. I just want to make sure that if you have a question.
Thank you for this very interesting talk. So when you talk about the mouse connectome, I think one of the challenges that we face is also the fact that each mouse is different, right? There are on the individual level differences, even on the mesoscale there are significant differences. How do you plan to accommodate for this? And is this a challenge at all for you?
Oh yeah, absolutely. We don't want one mouse connectome. We want many mouse connectomes. And I think at E11 we take inspiration from genomics about this. The first human genome was very expensive, but new technology unlocked cheaper and cheaper genomes to the point where now it's like the $1,000 or the $100 genome. And so the technology that we're building is highly scalable in a way that we think will actually deliver much lower cost floors than other approaches.
So you mentioned scale, and my question is, who could be the customer that will be ready to fund a large parallel effort where you just put thousands of microscopes at work at once?
Well, I think at this point in time, it's about building confidence that if you bought thousands of microscopes, you could actually deploy them efficiently. But I think the goal of the technology should not be to try to do a Manhattan project, because as we've observed, it's really hard to do a Manhattan project these days, at least using government funding. And so instead, the goal is to design your technology to be so good that you don't actually need to get together Manhattan project style funding.
Awesome. Thank you so much. Really appreciate it.